In this module, we shall look at a direction of generalization of the linear model which will lead to the generalized linear mixed model. Now, you have already been introduced to the linear mixed model in the modules on longitudinal data analysis. In this module, we will first briefly step back and recap what we know about the linear mixed model. If you remember, estimation for this model is done by maximum likelihood, and we have also introduced a related but not necessarily identical concept called restricted maximum likelihood. We shall generalize to the case where the outcomes are from the one-parameter exponential family, and we shall see that although in principle maximum likelihood can continue to be applied here, in practice application is difficult due to the presence of intractable integrals. This will lead to a method called penalized quasi-likelihood. We shall also look at a list of applications of the generalized linear mixed model, which in fact is very comprehensive. And finally, we will look at a data example, which we shall fit using the GLMM PQL routine in R. We shall now take a more detailed look at the generalized linear mixed model. Now, you have seen several precursors of this model in some other papers in the MSc curriculum. The first is the mixed model in the paper on linear models. You have first been introduced to random effects models, where you have considered yields, for example, which were taken from some sample locations. However, the purpose of the inference was not to concentrate on those sample locations, but to make inferences about a larger target population from which these selected yields had been taken. When you have factors, some of which are fixed and some of which are random, we come across the simplest example of the mixed model. A second example, which you have seen before, which motivates the generalized linear mixed model, is from something which is shown on this slide. So this is an example from the weight of pigs dataset in R. We are looking at the weight of several pigs, measuring this longitudinally over weeks, and in this graph we have plotted how the weight of the pig varies over the number of weeks. The regression model corresponding to this dataset is written in this first equation. So as you can see from the data, growth rate of pigs remains more or less the same. However, it appears that each pig starts out from a different point at baseline. We can model this by saying that there is a constant coefficient beta 1 per week for every pig. So note that beta 1 does not depend on I, where I denotes pig and j denotes time point. To accommodate the random intercept, we can write this as beta naught plus ui, resulting in an intercept beta naught I, which is equal to beta naught plus ui, and which varies across I. We could have stopped here, but not making any further assumptions about beta naught I would lead to a very large number of parameters. So in this case, 48 parameters, and hence poor inference. To reduce the number of parameters, we further make the assumption that the ui are normally distributed independently of the epsilon ij. So here is the general form of the linear mixed model. Note that for the linear model, y is equal to x beta plus epsilon, where we assume that epsilon follows a normal distribution with mean 0 and variance sigma square I. So typically for purposes of inference, epsilon is assumed to be normal. It is not strictly necessary, because even if epsilon is not normal, the inferences follow from the least squares. In any case, here I have introduced an additional component of the design matrix. So the linear mixed model is written as y equal to x beta plus epsilon plus an extra component which is zu. So Z is a design matrix, and the coefficients of the columns of this design matrix U are assumed to be random with mean 0, variance G, and they are uncorrelated with the epsilon. As for the linear model, we do not strictly need to assume normality, although more often than not, we do assume this. So inference for the linear mixed model can be effected through the principle of maximum likelihood. If we assume normality of U and epsilon, then the log likelihood of the data is given on the second line of this slide. So it looks like the usual normal log likelihood, the usual multivariate normal log likelihood. The variance V is the covariance of Y, and it follows from the first line of this slide that this is given by ZG Z prime plus R. For inference in this model, we first need to estimate all the model parameters. It turns out that the estimate of beta has a closed form expression and looks very much like the GLS estimator. So beta hat is equal to x prime V inverse x whole inverse x prime V inverse y. This assumes that the estimate of V is known. In practice, V is unknown and beta and V must be estimated iteratively. So to estimate the variance parameters in V, we can write the profile likelihood of V, which results in the expression given on the second and subsequent few lines on this slide. However, it turns out that maximizing LPV to get the maximum likelihood estimates of the parameters in V is not necessarily a very good idea, and the resulting estimates can be biased. So we consider something else which we have denoted by LRV equal to LPV minus half log x prime V inverse x determinant. This is called the restricted likelihood, and it leads to an estimator which is called the restricted maximum likelihood estimates. Now it is not enough to just estimate the fixed parameters. We also need to get some idea about the random component. Now note that the U's are random, and as such they cannot be estimated because the idea of estimation is tied to a fixed parameter. However, we can predict them. So by making a distinction between prediction and estimation, I mean that the best predictor of, say, a linear function L prime beta plus G prime U is given by L prime beta hat plus G prime U hat, where the expected sum of squared deviations, which is the prediction error, is minimized. It turns out that for the best answer to this question is given by the earlier form of beta equal to beta hat and U hat replaced by expectation of U given Y. If we use the normality and the properties of conditional and marginal normals in linear functions, it turns out that U hat is equal to G Z prime V inverse into Y minus X beta. So this allows me not only to make inferences about the fixed parameters, but also to make predictions about future values. So the 2-point summary for the linear mixed model is that fixed effects and variance parameters are estimated typically using ML for the fixed effects and REML for the variance parameters, although ML can also be used for the variance parameters. And the random effects are predicted using the principle of best prediction. We now want to generalize this to the case where we have generalized responses. So this means that my outcome Y is no longer normal or no longer continuous, but comes from the one parameter exponential family. So here, for example, is the probability density or mass function of the one parameter exponential family written in the canonical form. Now note that the linear predictor is now replaced by x beta plus zu, And I also make the additional assumption that U follows a multivariate distribution with mean 0 and variance covariance matrix G. For estimation in this case, we first need to estimate the fixed parameters beta hat and G hat. As before, we can use the principle of maximum likelihood estimation. However, if we work through the mathematics, the expression for the likelihood is as given on this slide, and we see that it is not as simple in the linear case because we now have an intractable integral as part of the likelihood. To get U hat, we can, as before, use the principle of best prediction. But again, although we can work this out in theory, when we write out the expression, it is not easy to compute this due to, again, to the presence of intractable integrals. These intractable integrals arise due to the fact that U follows a distribution, it is random, and it must be integrated over. A principle of inference which gets around this is penalized quasi-likelihood, or PQL. This has been very well discussed and developed in a seminal paper by Breslow and Clayton published in 1993 in JASA, which in fact is one of the most cited papers in statistics. So the idea of penalized quasi-likelihood is to approximate the integral by a Laplace expansion, and it can be shown that the resulting answer leads to maximizing the criterion given on the last line on this slide, where the first term is the deviance and the second is like a penalty and very closely related to the log likelihood of the U. Hence the name penalized quasi-likelihood. Now, strictly speaking, Breslow and Clayton do not assume that Y follows the likelihood which we have been using, but they make assumptions about the mean and variance of Y. So, if we do not believe the likelihood assumption to be true, we get quasi-likelihood estimators, and if we believe that these results indeed come from the likelihood, then the estimators which we get are maximum likelihood estimators. Some areas for the applications of generalized linear mixed models. The first is longitudinal data analysis. The example which I have shown you on this paper is the weight of pigs, which is a continuous outcome. We could as well have considered a count. So there is a famous example in R in some of the longitudinal data packages, which looks at the number of seizures for patients on a particular kind of medication. So this is a count variable and it is followed longitudinally over time. So the generalized linear mixed model could be one way of modeling this data. The second is spatial modeling. So here again we can look at some binary phenomenon. So say for example the presence or absence of a particular mineral over spatial covariates, so spatial locations. The correlation in this example arises from the fact that locations which are closer to each other will tend to be correlated, while locations which are further apart will tend to be less correlated, and it can be shown that the use of a random effect in the mixed model can account for this correlation. Smoothing, so this is same as spatial modeling but along one direction only. We wish to smooth a scatter plot, and here again it can be shown that one way of smoothing is to fit a generalized linear mixed model, and it can also be shown that the variance of the mixed model turns out to be the smoothing parameter. Generalized linear mixed models can also be applied to clustering. So for example, we might, instead of collecting a complete random sample, first select some families and then interview a few members of the same family. So say for example, we are looking at dietary habits, and instead of looking at a random sample of say 100 people, we could look at 20 families and interview 5 people from each family. So in this case, there would be some clustering in the sense that observations from the same family would tend to be similar. Such clustering can also be modeled using generalized linear mixed models. Finally, we can look at GLMMs as a tool for overdispersion. Overdispersion refers to a situation where the model specified variance is different from the nominal variance. There are many ways of accounting for overdispersion, but one way could be to introduce a random effect and estimation via the generalized linear mixed model. Let us now look at a concrete example. In this example, my outcome is balance. So I'm looking at balance for a number of subjects which has been measured on an ordinal 4-point scale. For each subject, it has been observed for 2 different surfaces and for restricted and unrestricted vision. So here we can see that 40 subjects were studied, 20 of them were male, 20 of them were female. Their ages ranged from 18 to 38. Each subject was tested twice in each of the surface and eye combinations. For more of this data set, you can refer to the Australasian Data and Story Library. So here is a snapshot of the data. I have for each subject observations on their sex, age, height, weight, surface, vision, and finally a score indicating their balance. Now note that there are multiple observations per subject, and we can expect these observations to be clustered in the sense that same observations on the same subject, repeated observations on the same subject will tend to be more similar. So to begin with, instead of looking at my 4-point balance, let me dichotomize this and create a binary variable. So this is what I have done by creating the variable stable and including it in the dataset CTSIB, which contains this data. Summary CTSIB will give me a summary for each of the variables. To begin with, I could perform a very naive analysis where I simply ignore the subject effect. Now this we know can be done using the GLM function. So here I have considered a regression of stable on sex, age, height, weight, surface, and vision. My family is binomial and the data is CTSIB. We know that the canonical link for the binomial family is the logit link, so this will fit a logistic regression. And if I type summary GF, then will get the log odds ratios which are given as part of the output here. Another perhaps somewhat less naive effort could be to include subject as a fixed factor. So here again this can be done using the GLM function. As before, I have regressed table on sex, age, height, weight, surface, vision, and included subject as a factor. As before, I use the logistic link. I can do an ANOVA of the 2 models, and we can see that the chi-square for this ANOVA is significant, suggesting that it is necessary to make some kind of adjustment for subject. However, the adjustment which we have made here by including subject as a fixed factor is probably not a good one because we have introduced a large number of parameters. We can conduct a bias-reduced logistic regression and see that indeed there is some confounding by subject. So one way out is to fit a generalized linear mixed model, and this is what I have done on the next slide using the function GLMM in the mass library in R. So in this piece of code, I first call the mass library, and then I use the GLMM function to fit a regression of stable on sex, age, height, weight, surface, and vision. As before, my family is binomial and my data is CTSIB. But I now have one extra component of the syntax which says that random is equal to tilde 1 within subject. Now you have seen similar kind of syntax when you have considered fitting a linear mixed model. What this says is basically to include a separate but same intercept within each subject. If I fit this model and if I ask for a summary, I get a big piece of output. So the first part of output is giving me the formula. It is telling me that the random component consists of a random intercept per subject. The standard deviation for this intercept is 3.06. So these relate to the parameters in G. The residual standard deviation is 0.59. So this is the parameters in R. And finally, here is a summary of the fixed effects. So as for a LM or an LME, I get the value, the standard error, the DF, the T value, and the P value. There is a lot more which I can do for GLMM analysis. For example, I can fit an ANOVA. I can look at several prediction criterion. I can look at post-model fitting diagnostics. But all these are outside the scope of the MSc syllabus, and for further references, you are directed to look at the document and references as part of this module. In this module, we have introduced the concept of the Generalized Linear Mixed Model, or GLMM. This is an extension of the linear mixed model which you have been introduced to in the papers on longitudinal data analysis. In case of the linear mixed model, we can apply maximum likelihood and restricted maximum likelihood to estimate model parameters. In theory, we can also do so here, but we have seen that intractable integrals arise, and hence it is necessary to introduce new tools. We have introduced the penalized quasi-likelihood, seen how inferences can be made for the generalized linear mixed model, looked at a list of applications where the generalized linear mixed model can be employed, and seen also that this list is very vast. Finally, we have looked at a data example where we are looking at outcomes which are correlated because they are on the same subject, and we have used the GLMM PQL library to fit a generalized linear mixed model which allows for correlation within the same subject.